Hi, welcome to this second video for Chapter 2. We're going to be talking a little bit more chemistry, but we're going to be talking specifically just about water and about the pH scale. So this corresponds to your textbook modules 2.5 and 2.6. In the last video, we ended our discussion talking about different types of chemical bonds. We spent a lot of time talking about the difference between ionic bonds and covalent bonds. When it comes to water, remember that water is a polar covalent compound. That means that the atoms within a water molecule, the hydrogens and the oxygen, they don't share their electrons equally. So if we look at a diagram, kind of remind us what that means, is when, again, we look at a diagram of water. Here's the oxygen, here's the two hydrogens. Here's kind of a simplified diagram, the two hydrogens and the oxygens. The oxygen carries a slight negative charge because it pulls the electrons closer towards itself. Remember that electrons are negative, so if they're pulling electrons, it's pulling a negative charge. What that leaves behind is a slight positive charge on each hydrogen because they are losing negativity, so to speak. So the result is you've got a negatively charged oxygen and a positively charged hydrogen and another positively charged hydrogen over here. This creates the two poles, or the opposite ends, of a polar compound in the case of water. Things that are nonpolar, they don't do that. They share their electrons equally, so there's no unequal distribution of charge. So because water does do that, it has an uneven charge distribution. If you take several water molecules and they've all got this same unequal distribution going on, they all have a negative oxygen and positive hydrogens, the result is that you can start to have a weak attraction between water molecules. So you can have the positive end of one molecule being attracted to the negative end of another water molecule. Those weak attractions between polar molecules, those are referred to as hydrogen bonds. Why do they call them hydrogen bonds? Well, because usually it's the positive hydrogen of one molecule being attracted to the negative part of another molecule. I'll show you what I mean in this particular diagram. Here's several water molecules. Here is the hydrogens of these two. Again, they are positively charged. Here's a separate water molecule, the oxygen being negatively charged. And notice that the hydrogen here is attracted to the negative oxygen. So this is what creates our hydrogen bond. Same thing going on here. You have the opposite charged poles of two separate water molecules being attracted to one another. The hydrogen of one being attracted to the negative end of something else, of another water molecule. That creates another hydrogen bond. Water molecules, they have a tendency to line themselves up so that the negative oxygen always faces the positively charged hydrogen on a separate molecule. That's what creates the hydrogen bond. If you have lots of this going on between all your water molecules, you almost have like a network of hydrogen bonds happening. And so every single one of these molecules is probably going to be involved in more than one hydrogen bond. And so because water does this, we say water is polar, has those opposite ends. Because water is polar, that's going to create some unique properties for water that we don't always see for other compounds that are similar in size to water. The first thing is that water is a liquid at room temperature. That's really easy for us to take for granted. Why does that result? Well, remember that a single hydrogen bond, one all by itself, is very weak. But because water, an individual water molecule, will form lots of hydrogen bonds, it forms this network. All of a sudden you have the collective strength of a bunch of water molecules forming many hydrogen bonds, and so you have this network of bonds. And so a network of hydrogen bonds means that in liquid water, hydrogen bonds, even though they break, they can reform constantly. So the water molecules on one end, they might be, breaking their hydrogen bonds, but on another case, they're reforming those hydrogen bonds at the same time. So any particular water molecule can be reforming, breaking, reforming water or hydrogen bonds all of the time. So because water can do that, this means that water, whoops, wrong way. This means that water can, here we go. This is a slide I'm looking for. Because water can form those hydrogen bonds through a big network, this is what makes water a liquid at room temperature. Now, to fully appreciate this, consider that water, H2O, if we could weigh the mass of one molecule, we would say that it weighs 18 atomic mass units. Where do we get that 18 from? If you look at your periodic table, each hydrogen has a mass of 1. So we have 2 of them, and the oxygen has a mass of 16. So 2 plus 16, that's where we get our 18. Well, if we compare that to other gases, nitrogen gas, which is N2, that means there's 2 nitrogen atoms that are bonded together. Each one of them weighs 7. Its atomic mass is 7. So 7 times 2 gives us 14. Well, nitrogen gas is the major constituent of our atmosphere. Every breath that you take in is not mostly oxygen, it's actually mostly nitrogen. About 80% of the air around us is nitrogen. Well, nitrogen weighs a little bit less than water, and it's a gas. Carbon dioxide, something that we expel every time we exhale, it weighs 28 atomic mass units. Again, where do we get that? One carbon weighs 12. One carbon weighs 6. Each oxygen weighs 8. So if you add the 2 oxygens plus 1 carbon, that's 28. 28 atomic mass units. And it's a gas. Oxygen gas itself is 32 atomic mass units. So if you compare nitrogen, carbon dioxide, and oxygen, these are all somewhere in the vicinity of the same mass as water. How come they're gases and water is a liquid at room temperature? The answer is because water is a polar covalent compound. Nitrogen, carbon dioxide, and oxygen, they are all non-polar. In other words, they all share their electrons equally within the molecule. So as a result, they don't form hydrogen bonds. If those compounds formed hydrogen bonds, they would be liquids at room temperature too. But water, it's the only one that's light enough and has this unique arrangement of its electrons to form these polar these polar attractions within itself, and that gives rise to it creating hydrogen bonds, which keeps it a liquid at room temperature. Because water is also polar, that means that water is less dense as a solid versus when it is a liquid. Might surprise you that water is less dense as a solid as compared to a liquid. Why does that happen? Well, the end result really is ice floats. You know, it's an easy way to say water is less dense as a solid. Ice floats. Well, how do you explain that happening? Well, when water molecules freeze, those very weak hydrogen bonds, they start to stabilize, and they begin to hold those molecules slightly farther apart from each other. Remember that in a liquid, the molecules are almost in a sense sliding across and over and around each other, constantly forming, breaking, and reforming those hydrogen bonds. But when water freezes, those hydrogen bonds are kind of locked in place in a very rigid lattice structure. And so you have areas between molecules where there are no other molecules. In fact, there's nothing there. It's empty space. It's trapped air in a sense. And so this trapped air between the various molecules is what causes water to be less dense as a solid. This is why ice floats. And so another way to think of this is that a chunk of ice compared to the same volume of liquid water, that chunk of ice will actually have fewer water molecules in it than liquid water. Well, why does this matter? Why is it important to living things? Think about large water systems, like, well, an ocean, for example. When we think of oceans and ice forming in the oceans. Well, ice will form at the North Pole and the South Pole, the Arctic and the Antarctic, at each hemisphere during the winter months. Of course, the winter months for those places on planet Earth. But that ice, it'll recede in the summer, but it won't completely disappear. And the formation of the ice during the winter, it traps some of the fresh water in it, and that salty water that's left behind, it will sink and flow back to the equator. And what that does is it helps cause some of the water currents that we see in the ocean. Sea ice itself can also act to protect the coastlines from erosion, particularly wind erosion and water erosion. In the summer, when that ice melts, the melting of the ice also changes the salinity of the water, and it actually stimulates the phytoplankton, which are the bottom of the food chain in aquatic systems, causes them to go into bloom, and they multiply and they reproduce at a great rate, and that provides a lot of nutrients for the other organisms that feed on that phytoplankton. And so in a sense it causes, life to spring in that area. So the formation of sea ice, the melting of the sea ice, and it's an important part of the biological functions that are happening in the environment that contribute to those living systems. Because water is also a polar molecule, we say that water is the universal solvent. What that means is at given time, water can dissolve just about anything. Why can water do that? Because the polar ends, or the oppositely charged ends, they align themselves around whatever they're dissolving, and they can pull things apart quite well. You can see this in the diagram here at the bottom. Why salt dissolves so nicely in water is that salt, remember from our previous video, salt is an ionic compound. That means that the metal sodium has a positive charge, and the non-metal chlorine has a negative charge. If you look real closely at my diagrams, the water molecules that surround either the sodium or surround the chlorine, they have oriented themselves so that the positive end is attracted to the negative end, or in the case of the sodium, the negative end is attracted to the positive ion. And so you can see how water acts like a magnet to pull apart just about anything that we try to dissolve in it. So given time, water can dissolve just about anything. One of the neatest properties of water is its ability to store heat. We say that water has a high heat capacity, and heat capacity is a way of describing how well a substance will absorb heat and store heat without actually changing temperature. Water has this awesome ability to take energy and just kind of keep it within itself, but water itself will not change temperatures. In fact, if water does change temperature, if it gets hotter, even by a few degrees, it has done that because it has absorbed an excess amount of heat. So when we look at lakes or rivers and we measure their temperature, if we see them increasing 5 degrees, that indicates that there's a lot of heat, extra heat in that system, and we often wonder where's that extra heat coming from. Because even a single gallon of water will absorb a tremendous amount of heat before it actually increases in temperature. By the way, the converse is also true. Water will actually release a lot of heat before it changes in temperature. So this kind of neat ability for water to have that heat capacity means that water is a good way to regulate temperatures, either within living systems like us, or if we think about our oceans over the whole planet, the large amount of water on our planet means that our temperatures are fairly stable. We don't have extreme temperature changes all over the planet going on all the time. We ourselves can use water to regulate our own temperature. Perspiration is basically evaporative cooling, so that if we get too hot, water can form on the surface of our skin, and if that water actually absorbs so much heat from our bodies, like in the picture, so here's my arm, if I've got water forming on the surface of my skin, in the form of sweat, perspiration. If that sweat actually evaporates, like in this guy's picture right here, it's taking the heat with it. Water molecules, we also describe them as being cohesive. That means that they can stick together and they'll kind of stretch themselves across a surface, and they'll create, in a sense, a tight skin, almost like a drum, a tight skin of molecules. That tightness, due to its cohesiveness, we call that tightness surface tension. And surface tension explains why little tiny insects, like a wolf spider, why they can walk on the surface of water so effectively is because they're walking across that tight skin. The way they distribute their weight, like if you notice our little spider right here, he distributes his weight over a fairly large area. And so even though gravity's acting on him to press him down, the surface tension, because it's so tight, is actually holding him up. If we did not have all of our center of mass, or our weight, in just over our 2 feet, if we could spread it out effectively like a spider, we could, in a sense, walk on water as well. Water also has the ability to climb thin tubes. We say that ability to climb thin tubes, that's referred to as capillary action. This is especially important to trees, because trees are basically a system of very long, thin tubes. So trees do not actually have to pump water from their roots all the way to the tip of their leaves on the very most extreme parts of them. Water itself, because they're polar, they have little magnets, they can climb thin tubes. Not only do they stick together, but they stick to other surfaces, and so they climb the surface and they climb each other, almost like monkeys climbing a tree, and they can climb all the way to the very top of that little test tube. They can overcome gravity to some extent. They can climb all the way to that top of that little tube to deliver water and any nutrients dissolved in the water all the way from the roots to the very top of the tree. We also use water as a basis of the pH scale. You've probably heard of pH as a measure of how acidic something is. Well, how does the pH scale come out of water? Well, the pH scale comes from the breaking up or the dissociation of a water molecule. Water, under certain conditions, will break apart into, believe it or not, a strong acid and a strong base. So here in my diagram, here's a water molecule breaking up or dissociating into the hydroxide ion and into the hydrogen ion. Hydroxide is a strong base. Hydrogen ions are strong acids. And so we measure how many of these are in a solution, and that is what determines the pH of something. So the concentration of hydrogen ions in an aqueous or a water-based solution, where we take something and dissolve it in water, that is what determines the pH of something. So definition of pH means something has to be dissolved in water, and that thing, whatever's dissolved, is going to be giving off hydrogen ions. The more hydrogen ions that are given off, the lower the pH. So another way to say this is the pH is, we measure how acidic something is. So looking at this diagram from your textbook to kind of measure or explain pH, here's the pH scale. Now I mentioned previously that the more hydrogen ions, the lower the pH value. The pH scale, it runs from 0 to 14. Right exactly in the middle is 7. So anything below 7 is considered to be an acid. Anything above 7 is considered to be a base. The difference between a pH of 4 versus a pH of 5, it's not 1 degree of difference. It's actually a 10-fold change in the concentration of hydrogen ions. So what that means is that if we compare a pH of 4 as compared to a pH of 5, the difference in the number of hydrogen ions is 10 times. Believe it or not, a pH of 4 has 10 times more hydrogen ions than a pH of 5. I'll show you what I mean on this next slide a little bit. So if we consider just values below 7. These are acids. Acids will have a pH between 0 and 7. Because, again, of the way that pH is calculated, strong acids are further away from 7. That means that these guys have lots of hydrogen ions. Weak acids are closer to a pH of 7. That means that there are very few, relatively speaking, there are fewer hydrogen ions on this end of the scale as compared to this end of the scale. At a pH of exactly 7, a substance is neither acidic nor basic. They're considered to be exactly neutral. What that means is the amount of hydroxide ions, the OH minuses, and the ones that we're concerned about, the hydrogen ions, they're equal to each other. So there's as many hydrogen ions, as many strong acids, as there are hydroxide ions or strong bases at a pH of 7. The further you get away from 7, the greater or the more hydrogen ions you get. So remember that hydrogen ions, they are what determine how acidic you are. So if you've got more hydrogen ions on this end, you have stronger acids. Fewer hydrogen ions on this end are weaker acids. So if we compare things like tomatoes versus strawberries versus lemons, all of those things are delicious. Lemons happen to be the most acidic. They're lower on the pH scale. That means you're going to have more hydrogen ions. Tomatoes are going to be less acidic as compared to these two, of course. That means you're going to have fewer hydrogen ions. If we could throw black coffee into the mix with a pH of 5, black coffee has the fewest hydrogen ions compared to coffee, tomatoes, strawberries, and lemon juice. Battery acids, yeah, the stuff that runs your cars, they have a pH of about 1. That's a really strong acid because it contains hydrochloric acid. The same thing found in your stomach, by the way. Hydrochloric acid, battery acid, has a pH of about 1. Black coffee has a pH of 5. Here's a quick question for you, or I guess 2 quick questions. First, who's the stronger acid, battery acid or black coffee? I hope you said battery acid. If you said battery acid, you're correct. This is the stronger acid. My next question is, how many times stronger? Well, a pH of 1 and a pH of 5 has a difference of 4. But remember that it's a 10-fold difference. So that would be 10 to the negative 4, or a 1 with 4 zeros after it. That means that battery acid has 10,000 more hydrogen ions as compared to black coffee. Crazy, huh? What about the other end of the scale? What about the other end of the scale? Above 7. Things that are above 7 have fewer hydrogen ions than anything below 7. In fact, there's so few that we describe these things as bases. Strong bases have a pH further away from 7 as compared to weak bases. Remember that 7 is exactly neutral. Our hydrogen ions and hydroxide ions are equal in concentration. The reason these are such strong bases is not only because we have so few of the hydrogen ions, but also because we have lots of hydroxide ions on this end. Our definition of a base is going to be any chemical that when we put it in water, water is part of that definition, we lose hydrogen ions. So these compounds up here, because they have a pH that's above 7, they're going to be basic. Looking at lye, that's the most basic thing listed on this scale. It's going to have the fewest hydrogen ions. Household bleach is going to have more hydrogen ions than lye. Ammonia is going to have more than bleach. So the further you get to 14, the fewer the hydrogen ions that you're going to have. By the way, looking at baking soda right here has a pH of 9. Compare that to lye, which has a pH of 13. Who's the weaker base? Baking soda or lye? Who's weaker? I hope you said baking soda. If you said baking soda, you're correct. It's the weaker base. My next question is, how many times weaker? What's the difference in hydrogen ion concentration? Well, the difference between 9 and 13 is 9, 10, 11, 12, 13. That's 4. Again, that's a 1 with 4 zeros after it. There is a 10,000 time difference of hydrogen ions between baking soda and lye. Who has more hydrogen ions? Who's got the 10,000 extra? I hope you said baking soda. It's the weaker base. It has more hydrogen ions. The stronger base, the lye, will have fewer hydrogen ions. Interestingly, you might have noticed that human blood is not exactly neutral. It's got a pH of just above 7, just above it. Why is that? Oh, I'll answer that question in a couple of slides. Actually, I'll answer it in one slide right here. Why is the pH of blood just above 7? Well, living things, they cannot tolerate wide swings in pH. Living things have inside of them buffers which help reduce changes in pH. You're no exception. Your blood has buffers inside of it that counteract a drop in pH. Most of the time, our drop in pH, in other words, we become more acidic, happens during exercise. Why does this occur? Because of carbon dioxide. Carbon dioxide, when it dissolves in water, it forms carbonic acid. Whenever you're exercising and you're trying to get in better shape, if you are not in a good fitness level for however intensely you're exercising, if you're breathing really hard and you can't get rid of carbon dioxide fast enough, that excess carbon dioxide will stay in your system and it will cause your blood pH to drop. In other words, the carbon dioxide causes carbonic acid, and carbonic acid causes your blood pH to drop. So to counteract that, because a low pH is dangerous, it causes your brain to not work very well. It shuts down some of the proteins. It can even shut down some of the chemical reactions. To counteract that and protect you from suffering brain damage, literally, your body starts the pH of its blood at a little bit above 7, but then it adds some buffers in order to keep it from falling below 7 anyway. Would you believe that one of the buffers that your body uses is good old baking soda? It helps keep the pH of your blood slightly above 7 so that you don't pass out from too much carbon dioxide forming carbonic acid in your tissues when you're doing intense things like exercise. What about pH changes in the environment? Well, pH changes in the environment can be serious as well. And again, we'll look at carbon dioxide. When we think about atmospheric carbon dioxide, how much we have around us, carbon dioxide in the atmosphere, not only can it dissolve in watery tissues inside of systems, and it can also dissolve in water such as lakes and oceans. And carbonic acid can be formed also in lakes and oceans just as easily it can be formed in your tissues. And so if we're considering like a lake or an ocean and there's excess carbon dioxide above it and it's kind of settling into the water, forming that carbonic acid, lowering the pH, that can be dangerous to the organisms, plant life, animal life, which are living in that water. Most of them cannot tolerate the low pH. In the case of coral reefs, most coral reefs are made up of a substance called calcium carbonate. Basically chalk, calcium carbonate. Well, calcium carbonate is solid in water, except that when the pH of the water falls below 7, calcium carbonate begins to dissolve. So low pH in marine systems and oceans can be extremely detrimental to coral reefs. It literally causes them to dissolve away, and that can impact not only the coral itself, but all the organisms which depend on the coral. Right now, we know that atmospheric carbon dioxide levels are a problem in our environment. They're rising due to industrialization and because we're losing forests, deforestation. And so there's a lot of worry about what is going to happen to our ocean systems over the next 100 years due to rising levels of carbon dioxide. I'm going to tell you a little secret about atmospheric carbon dioxide. While industrialization and deforestation, they get a lot of attention, the biggest source of atmospheric carbon dioxide is the ocean itself. Because it turns out not only can carbon dioxide dissolve into the ocean, it can also evaporate out. So the carbon dioxide that's around here, it's not only coming from us exhaling, other animals expelling carbon dioxide, volcanoes expelling carbon dioxide, it's also coming from the ocean itself. Now, why doesn't that get a lot of attention? Well, it's a natural process. It's a natural cycling of carbon dioxide into the ocean and then back out again. What is causing concern is that more carbon dioxide seems to be coming out than what's actually going in. And what seems to be the blame? Rising atmospheric temperatures. Because it turns out that when the temperature is too hot, carbon dioxide has a hard time dissolving into the ocean. Instead, it leaves. So our rising atmospheric temperatures could be the cause of excess carbon dioxide levels coming from the ocean itself. You add on top of that things that aren't taking carbon dioxide out of the atmosphere, like trees, removing trees through deforestation. That's counteracting the excess carbon dioxide in the atmosphere. And then we're adding more carbon dioxide from, again, industrialization. Lots of cars on the road, lots of factories producing things, a lot of waste. So it's interesting to think over the next 100 years, or even within your lifetime, the next 50 years or so, what do you think the impacts of excess carbon dioxide could be on our aquatic systems? Something for you to think about, something for you to consider. So I hope you've enjoyed this short video on water and pH. It's modules 2.5, 2.6 from your textbook.